Hi, I'm Mark Perry with Colorado Dam Safety. Welcome to our tutorial video overview of hydrological evaluation and design processes. So the purpose of this tutorial is to give you a 10,000 foot view of our new framework and processes for hydrological evaluation and design. So we've developed over the past 5 or 6 years, we've developed a lot of new methods for hydrology analysis. This tutorial won't go into the details of the methods, but it's intended to give you the high level overview so that we all understand where we're going with our hydrology analysis for Colorado dam safety purposes. So the easiest way I can summarize it is we now have two processes. The first is hydrologic risk analysis, risk-informed decision-making for the evaluation of hydrologic adequacy for existing dams. Okay, that's the first. The second process is determining inflow for design, determining inflow design floods, IDF criteria, hydrologic hazard category to determine your IDF for use in a design project for new dams, raises, new spillways, and appurtenances. Okay, but first let's look quickly at the various methods we have developed that the new processes are built on. And like I said, we won't get bogged down in the details here. The details exist other tutorials and in the guidelines themselves, but let's just do a quick rundown. So firstly, we developed our 2020 rules and regulations for dam safety and dam construction. Mainly Rule 5.2 is for that the rule that covers the state engineer's safety evaluation of existing dams, which comes from authority under statute 3787-107. 5.2 lays out the rule for evaluating dams by potential failure mode analysis or risk analysis, risk-informed decision making. Okay, then Rule 7.2 deals with design standards. So Rule 7 is design. 7.2 lays out the design standards, IDF criteria for hydrologic loading. We also developed our guidelines for dam breach analysis, which you'll use in our guidelines for hydrologic hazard analysis. That's consequence analysis. We have our guidelines for use of a regional extreme precipitation study, REPS, rainfall estimation tools. And that feeds into rainfall runoff modeling, which is in our guidelines for hydrological modeling and flood analysis. And finally, for the risk analysis, risk-informed decision-making, that all feeds into our guidelines for use of comprehensive dam safety evaluation, CDSE, risk assessments, and risk-informed decision-making. Okay, let me show you quickly where on our Colorado Dam Safety web page the various rules and guidelines reside so that you can go to those and find them, and then we'll get into this overview of our hydrological processes for evaluation and design. All right, so go to our Colorado Dam Safety. You can Google it or use your search engine. Our Dam Safety web page. If we scroll down, first of all, the rules are here under the drop down for rules, and you'll find the link to a PDF of our 2020 rules and regulations for dam safety and dam construction. Go up a couple levels and you can drop down our guidance documents, and there you'll find all the ones that I mentioned in the previous slide and a lot more. All right, and then up to the blue bars, we have reducing likelihood of dam failure by following best practices. So if you drop that down, there's a lot of interesting stuff in here, but of interest to us here that we have an overview of hydrological evaluation and design processes document that is the basis for the tutorial presentation here today. And that is kind of buried at present. We'll try to bring it up more front and center, but for now, you can find it under that blue drop down of reducing likelihood of dam failure, go down to comprehensive dam safety evaluation tools, and you'll get to a Google Drive. And in that, you'll see Appendix B, overview of hydrological evaluation design processes. That's a PDF that you can download. Okay, so here it is, our overview of hydrologic evaluation and design processes document, the 10,000 foot view. The document has 2 flow charts, one for each of those processes I talked about, for risk evaluation of hydrologic adequacy for existing dams, and then a flow chart for the design flood process. And then it's in the document's in a flip chart type format, and it has just little flip chart summaries of each of the steps in each of the flowchart processes. Okay, so let's start with process 1, flowchart 1, the evaluation of hydrologic adequacy for existing dams. And as I said, that comes from Rule 5. Rule 5.2 is state engineers' methods for determining safe storage level for existing dams. And then 5.2.2, well, 5.2.1 is our normal safety inspection process, just inspecting dams, looking at performance history. 5.2.2 is this potential failure mode analysis, which we use for risk-informed decision making for safety evaluation of existing dams. Okay. So that leads us to flowchart 1. See across the heading across the top, risk-based evaluation, hydrologic evaluation, and consequences analysis for existing dams. So the question in red, the big red letters, is the study and evaluation of existing conditions. If it is, use flowchart 1. So this is flowchart 1, the process for safety evaluation of existing dams for hydrologic adequacy. Step 1 is to determine consequence estimation from hydrologic dam failure. So we're looking at potential failure mode, hydrologic potential failure mode. Most of our dams are earth dams. We're generally talking about overtopping dam failure. But we have other types of dams. There may be different critical hydrologic PFMs, but we do the dam breach analysis for that PFM and determine estimate life loss consequences. And that's by our guidelines for hydrologic hazard analysis, and we use reclamation's RSEM, reclamation consequence estimation method, to estimate life loss consequences. Then we go to the hydrology modeling for hydrologic risk analysis, evaluation of existing dams. We use the REPS probabilistic storms. I'm talking about the REPS Met Portal precip frequency tool. So we get the probabilistic storms from REPS. Remember, there's 7 AEPs, annual exceedance probabilities, 1 in 10 up through 1 in 10 million, and then there are 3 different storm types. So we have the 2-hour local storm, the small intense thunderstorms, 6-hour MECs, medium size, medium intensity, and then the long duration, 48-hour low intensity MLCs, or mid-latitude cyclone storms. 3 storm types, 7 AEPs, so that's 21 storms total. Get all those from REPS. Run those through a rainfall runoff model, which is our CSU SMA method, and then we do the reasonableness checks. So we're checking the model to make sure agreement with the observed flood record, with stream gauge, stream stats, peak flow envelopes, to get reasonable results. And that's all covered. Steps 3 and 4 are all covered in our guidelines for hydrologic modeling and flood analysis. Once we're sure we have a model that's given reasonable results and defensible results, then we run all the REPS probabilistic storms through the model and generate the peak reservoir stages by AEP, which gives us a hydrologic loading curve, also called the reservoir stage probability curve or hydrologic hazard curves. And I'll show you an example of that. So we have that. We have the consequence estimate for hydrologic PFM, life loss estimate, and then we have the likelihood of hydrologic loading, and that feeds into our decision-making process hydrologic risk analysis or risk-informed decision-making, where we under state engineer under Rule 5.2 determines if the dam is hydrologically adequate. Okay, so if the risk is acceptably low, no actions required. It's good. It's an acceptable risk under industry standards. If it's kind of moderate risk, there may be some non-structural improvements that an owner can make, an early flood warning system or emergency management, emergency action plan planning type of things to lower consequences. But if the risk is unacceptably high by industry standards, then we're talking about we'd be looking at structural improvements to the dam, and that would take us to Flowchart 2 design standards. A couple things before we get to that. So we have here in the gray hatched or dashed box a jumping off point for low hazard consequence dams. So if the consequences from hydrologic failure of the dam can be demonstrated to be low, then we want to make this easier. We don't want it to be put a bunch of owner resources or consultants or our resources into that. So if we can demonstrate low hydrologic hazard consequences, then we can evaluate the safety, hydrologic adequacy of the existing dam, really just by inspection. And what I mean is looking at the performance history, maybe some rules of thumb, maybe stream stats or sizing, looking at the capacity of the existing spillway, but not necessarily this full-blown risk analysis process for low hazard consequences from hydrologic dam failure. And we say that if it's in a rural area or just downstream rural land use or ag land use, then that low hazard consequences determination can be made by inspection. Okay, and so before we go to design, I want to walk through a couple of these steps in this risk analysis, hydrologic risk analysis process. Okay. So the first here is the reservoir stage probability curves or hydrologic hazard curves. So we've already determined the consequences, life loss consequences from hydrologic dam failure in that step 1. Now we go through the modeling, the REPS probabilistic storms, the modeling, and we generate these hydrologic hazard curves. Okay, so this is peak reservoir stage for each AEP storm, and then the 3 storm types. So here we're showing the blue curve is the REPS MLC 48-hour storms. The orange curve is the REPS MEC 6-hour curves. The gray one is the 2-hour local storms. Okay, and the controlling one, those can cross. Different storms may control at different AEPs, but the controlling upper line is is what we call this composite or controlling reservoir stage probability curve. Okay. Here we've plotted reservoir stage on the y-axis and then annual recurrence or average recurrence interval on the x-axis, which is just the inverse of annual exceedance probability. So we're looking at 10-year, 100-year, 1,000-year, 10,000-year, etc. And then we can plot different key elevations as horizontal lines. The critical one here is the dam crest elevation, and we'd be looking at, in this case, at the overtopping, dam overtopping PFM. And so we look at that controlling hydrologic hazard curve, and where it reaches the dam crest, that's incipient dam overtopping, and we could call that the ARI or AEP of dam overtopping. So in this case, let's say looks like it's about 75,000 years, or for average recurrence interval, or an AEP of 1 in 75,000. Okay, the next, we take that, having determined that likelihood of critical hydrologic loading for the PFM. So we go to our risk matrix which comes from our Colorado Comprehensive Dam Safety Evaluation CDSE guidelines, and we can plot that likelihood of hydrologic loading against the life loss consequences here on the x-axis. And so let's just say we were at life loss consequences of 50, and likelihood of hydrologic loading of 175,000, we said. So that would put us somewhere in here. And the yellow square just below this diagonal red line, which is the societally acceptable risk line. So like we said before, this kind of moderate area of risk, yellow, may allow may be acceptable to do some non-structural measures like an early flood warning system or better emergency planning to reduce consequences and get us to an acceptable level of risk. If we're down here in the green, if the risk plots, hydrologic risk plots in the green, it's okay. It's an acceptable level of risk by industry standards. But if the hydrologic risk plots up here in the red, structural measures are going to be needed most likely to reduce the risk to an acceptable level. Okay, so now let's go to the hydrologic design process. So I know this is the part that everyone wants to go to. That we're design engineers, we want to design and build things, and we kind of automatically jump to the inflow design flood. But that first step for working on any existing dams, that first step of evaluating hydrologic adequacy by hydrologic risk analysis is critical. And I want to reiterate that determination comes from the determination of hydrologic adequacy comes from the state engineer under Rule 5 and statute. Then if we're talking about existing dams, if we determine the dam is inadequate or an actionable level of risk, then we go to design. Otherwise, you might be going straight to design for a new dam enlargement, or any other modifications, say for spillway modifications due to concrete deterioration or condition, anything like that. So any design process where we're going to design and construction will be this, or any design project we're going to design and construction will be in a second process of determining inflow design flow. So let's look at Rule 7 in our 2020 dam safety rules. Rule 7.2 gives the criteria for inflow design floods. We have this hydrologic hazard category. We determine that by hydrologic hazard analysis, and then we group the consequences into one of 4 categories: extreme, high, significant, low, and assign a corresponding critical rainfall for the inflow design flood criteria. So extreme hydrologic hazard has a PMP storm or PMF flood. High hydrologic hazard has a 10,000 year flood. Significant hydrologic hazard has a 1,000 year flood, and then low hydrologic hazard has a 100 year flood. So these generally come from our reps rainfall estimate, and then rainfall runoff modeling. So these are hydrologic. The hydrologic hazard category is based on consequences from hydrologic dam failure. Again, generally talking about earth dams, generally talking about overtopping dam failure mode. All right, so let's go to Flowchart 2, which goes through this process of design, determining an inflow design flood for hydrologic design. So Flowchart 2 across the top, inflow design flood study. If you're doing an inflow design flood study for design of new dam or modification to existing dams, again, the big red letters at the top, is a study and evaluation of existing conditions, an existing dam, or is it a design project? If it's a design project, use this flowchart, Flowchart 2. It looks very similar to Flowchart 1, but there's a couple of key differences. Now, first one, we're still gonna do it's all still based on consequences from hydrologic dam failure. But in this case, we use our hydrologic hazard analysis guidelines, reclamation's RSEM method to estimate life loss consequences, or we can also determine non-life loss consequences at the same time, and then we group those into a hydrologic hazard category for purpose of determining the IDF criteria. The categories are discussed in our rules in Rule 7.2 and in Rule 4. But again, they're extreme, high, significant, and low. The purpose of the hydrologic hazard category is to give us to set the IDF criteria. Then you model that, get your IDF criteria, model that storm in, do the rainfall analysis for that storm in reps, model that in our rainfall runoff model, our CSU SMA method, and then we still need to do all the reasonableness checks. So you're going to still have to model other rep storms to do the reasonableness checks, to check against stream gauge analysis, frequency floods, stream stats, peak flow envelopes, to make the case that the CSU SMA model is giving reasonable results. We want to have reasonable inflow design floods, just like we want to have reasonable floods in the hydrologic risk analysis. So once we've made the case against the observed flood record that the model is giving reasonable results, we can use the inflow design flood that comes out of the model. Okay, so that then we carry into your decision making step, if you will, basically your design. So design of a new dam, enlargement modifications per the design standards and Rule 7. So we have just a couple kind of qualifiers here, I guess, with the dashed arrows. There is still potential for early flood use of an early flood warning system or improved emergency action planning to lower life loss consequences. Going back to step 1, there is that could be used to lower hydrologic hazard category, which would in turn lower your IDF criteria. And then this bottom arrow, what we've seen is that in some cases that deterministic reps PMP is very extreme compared to reps precip frequency. So it may plot the PMP rainfall may plot well beyond 10 to the minus 7, our most extreme precip frequency estimate. And if we are way beyond that, what we say is that PMP may be far in exceedance of likelihoods or risks of concern for dam safety. So what we have done is that we have the possibility of, in that case, of granting a waiver, a state engineer approved waiver to the PMP IDF criteria and substituting a lower risk-based IDF criteria in that case. All right, and as we had in Flowchart 1, again, we have a jumping off point for low dams with low hydrologic hazard consequences or low hydrologic hazard category. So again, we want to make this simple in this case, as simple as possible. We don't want to use owner and consultant and our resources on excessively on waste resources on low hydrologic hazard dams. So the simplifications here could be just using the IDF criteria is the 100-year storm, 100-year flood. So we could just go straight to using stream stats, or if we have a stream gauge, a flood frequency estimate to get a 100-year flood. And if you want to just design the spillway to pass a peak flow, then that may be it. Now, if you expect significant reservoir routing from a good sized reservoir, then you may still want to do the modeling, just compare the model to the 100-year, calibrate it in that way, and then use your model to do reservoir routing. But we want to keep that process simple for low hydrologic hazard category dams. Okay, that's the end of the overview of these hydrologic evaluation design processes. 2 main processes. Let's just recap what we talked about. 2 main processes. The first, hydrologic hazard analysis for the evaluation of hydrologic adequacy at existing dams. That's done by hydrologic risk analysis, risk-informed decision-making. We get consequences, life loss estimate, and likelihood of critical hydrologic loading. We plot those on a risk matrix, and we determine whether there's an actionable risk or whether there's not an actionable risk. And that determination is made by the state engineer's office under our authority to determine the safe storage levels for dams, so for existing dams. So Rule 5 and then Statute 3787-107. Now, if we determine there's an actionable risk, we go to a structural modification, spillway design project, raising freeboard, whatever, or any other design project. So a new dam, modifications of a dam, just spillway improvements for other reasons, concrete deterioration, what have you, Then we go to Flowchart 2, the process 2, the inflow design flood process to determine the hydrology for design. That's we determine consequences, fit those into one of 4 hydrologic hazard categories, get an inflow design flood criteria, model that inflow design flood, and that is the basis for your design. We talked about jumping off points in both processes for dams with low hydrologic hazard, so we're not wasting excessive resources on those. And then we talked about some of the qualifiers like potential to lower consequences through early flood warning systems. And we talked about the potential for a waiver to the PMP IDF criteria where REPS PMP is shown to be far beyond the risks of concern in dam safety when we compare it to REPS precip frequency.